Welcome, everybody, to the first workshop, part of our AI Revolutions Symposium. We have 3 workshops today, really 2 workshops. The first workshop here is going to be about understanding transformer models, understanding large language models. The second one is going to be more about how to use those models and using prompt engineering. And then the third is actually a hands-on session with the data science team to help you with crafting your own prompts to use these models in your work, in your research, in your teaching, or for your personal life. So thank you all for joining us today. The first thing I'd like to do is actually to change the title a little bit. So we keep on talking about understanding ChatGPT models. So and that's not wrong to think about it that way, but in actuality, ChatGPT is kind of like Coke, right? So it's just one kind of soft drink. It's not really all of the soft drinks. So really, if we want to talk about all the soft drinks, then generally you can talk about large language models. And with large language models, these are transformer models that have been trained on massive amounts of text. And because of this, have capabilities that are useful. But as we're going to learn about today, it doesn't really end there. As a matter of fact, there's a lot more that goes into the training of the models to make them useful. And this is important for us because it determines how we interact with them. It also raises up the problems that we have with them and the issues that might be hidden with them. So it gives you a good idea of their strengths and of their weaknesses if you understand exactly where they come from. But first, let's take kind of a big step back. So let's take a look at what we've called AI over the years, because it's really changed. And what I want to point out here is a couple of things that have changed, but I also want to point out the timeline here. First of all, we've been talking about AI for a long time. There have been times when we have decided never to mention the name AI because it simply didn't work and it was overhyped, so-called AI winters. And we can see since about the 1990s, we've been getting useful things that have been very broadly used. And then, 2010, we started to get useful things out of convolutional neural nets. What I'd like to point out here is that really, transformers are the underlying technology of large language models. So what's so different about transformers? Well, it can work with any sequence data, and we'll see that in just one moment. They're powerful general purpose learners. The other thing which is different is that they've really not been around for very long at all, less than 5 years. And as a matter of fact, the types of models that we're working with now, especially in their current form, closer to 3 years. So this is extraordinarily new technology, but technology that has been remarkably successful across a number of domains. They hold the top performing, they're the top performing models, transformer models, top performing models across pretty much any domain that you can think of. And with the release of ChatGPT in November of last year, we all of a sudden saw the utility and the power of using these models to solve a variety of problems. So main take-home message here is really, if we're putting transformers in the right place, transformers is really like, they start right here. It's just happening right now. So what changed? So we had decades. We had, all the way from the 50s all the way up until like 2015, where we could solve some problems and do some very interesting things, but really didn't have anything that we could solve general purpose problems with. So what changed? What's different with transformers than anything else here? Well, a couple of things. One, transformers are general purpose learners. So it's not just that they can learn on some structured data, they can learn on any sequence. So it could be language, and that's where large language models come from. We're going to be diving into that in just a little bit. But it can learn off of audio. It can learn off of protein sequences. It can learn off of images, because images are sequences. It can learn language from audio. Pretty much anytime you have a sequence, a transformer can learn it. So that's an important thing. Another thing is the approach to how we're training these models. And that is, instead of previously, like with convolutional neural nets, where you could use them to solve really interesting vision problems, but the training for that was millions of images, of labeled images. And that's how the first convolutional neural nets were trained. Transformers, we didn't do that. Instead, with transformers, what happens is it's self-supervised learning. So what does that mean? Well, really, it just means that you remove part of the data and you ask the model to fill in what's missing. So this doesn't require that you label anything. It doesn't require that you do a whole lot of work at all. It really is just a matter of, hey, model, fill in what's missing. And we're going to do an exercise with that in a minute, just so you can see what that really is like and how that works and how much you can learn from simply doing masked learning. And the final thing is transfer learning. All right, so here, way back here, when we had all these cool approaches, if you solved one problem, you solved one problem. This began to change, didn't change really until like 2010, when we started to work with convolutional neural nets and some with recurrent neural networks. And what happened here was that if you trained a network, a CNN, convolutional neural net, to solve a vision problem, then it turns out it could learn the next vision problem really fast. So you don't start from scratch anymore. You train on the millions of images, and then you build your cat detector. And it's really good. It only takes a couple of dozen images before you can get a really good cat detector. If you're concerned about cats and you want to be able to detect them in any image, great. It reaches top performance very quickly through transfer learning, meaning it learned about images from its previous exposure, and then the training proceeds very, very quickly without having to have massive amounts of labeled data. With transformers, and in here, then it's in vision and you can solve vision problems. Transformers, very much the same thing, but on steroids. So instead of just learning about images with transformers, and let's just take the example of text, with transformers, it learns not just about text-like tasks, it learns about the text. So the language in which the text is written, the concepts that are being discussed, the worldviews that are represented in the text that it's been given. So all of that is available to you to solve many different types of problems. So you have a transformer large language model that's trained on massive amounts of text over the internet, and you could use that to do sentiment analysis. Is this positive or negative? Hey, no problem. Hey, but you can also use it to generate a new type of recipe given these ingredients that you have. Not a problem. Why? Because the model has learned the context. It's learned about things like ingredients and nutrition and cooking and proper cooking temperature for a turkey. It probably even knows you shouldn't be dropping a frozen turkey into in boiling oil. It learns all of these representations. And that's what's so different about transformer models and large language models now, is that transfer learning has been taken to the next level. So pretty much any task that involves text is fair game, is possible, can either be accomplished or can be accelerated with the use of these models. So what changed? Now we have a very general purpose, powerful learner. We have self-supervised learning, and so it has a way of learning these different things. And finally, we have a way for the model to apply that learning in many different domains and many different areas. Let me pause here and see if anyone has a question before we dive further into this. What questions do you have? And you're welcome to unmute yourself or to put this into chat.
I have a brief question.
Yes, Raymond.
Okay, let's see. How do NLP and VS modality kind of intersect into the neural nets and the transformers for synthesis? Like, the way that I'm being taught as an example is we learned ML. I have experience with VS. I'm learning at NLP. Where do those kind of synthesize together to reach this nexus point?
Yeah, good question.
I'm trying to see if there's any missing gaps that I'm unaware of.
Yeah. Sure. No, great question. And we're actually going to see that in just a little bit, as a matter of fact. So the idea is that everything that's important for NLP is learned through self-supervised learning. And then it's all in how you use the transformer after that. And we'll see exactly what the transformer is doing in just one moment to sort of tie these together. But really, the important thing is the transformer is doing the learning, and then the transformer is also doing pulling back that information and then making generation of text. So, and we're going to see how that ties together in just a moment. So, great question. So, Paris, you had a question. Is human reinforcement part of transformer? It is a way to train it, and we're going to see that as well. Great catch on that. You're absolutely right. Human reinforcement learning so this is reinforcement learning from human feedback, is something which is critical for the performance of these models. And you're going to see how that plays in just one moment. And yes, it does make the models much better. Ken, our stable diffusion mid-journey, all based on transformers, they do have learning very similar to this. And some of them do have transformers as part of it, but there's another part too, but very similar in that all of these models learned about images and the semantics of images as well by the same kind of task. So self-supervised learning was one of them. Another way is a diffusion process where the model has to learn how to denoise the model, but very, very similar to this. And actually they're used in conjunction, but very much that idea that you don't have to label data. You have self-supervised learning, powerful learners, and then using that transformer learning. That same recipe is what we use for stable diffusion as well. Jack, you had a question, then I will get to you. When we say the model is learning, is the model actually making a neurological connection within its programming? So what's happening here is that the weights of the model are being changed. We're going to talk, we're not going to really see it, but we're going to talk how that happens. It's through back propagation. So when we train a model, then what's happening is it's effortful, it's computationally expensive, but we're actually changing the model. We're not changing, and in a sense, we're changing connections, right? Because we're changing weights between these artificial neurons. And that is sort of, that is taking the training and moving it into the weights. So there's, back propagation itself is not biologically based. It's a very different non-biological way of doing it. But yes, you're changing the connections in these large networks. And Dr. Ya, you had a question.
Thank you so much. I was just curious, what was it about OpenAI's approach that allowed them to arrive at this solution prior to everyone else? Was it just that the level of complexity and the amount of compute needed needed such a large investment, therefore it was just a higher threshold for anyone else to reach? Or was there something else that allowed them to just kind of march in here very disruptively, catching everyone's attention?
Yeah. This is really interesting, and we will get a little bit more to this in just one moment. But let me go ahead and mention that that what was not anticipated by everybody was what Paris, pardon me for mispronouncing your name, Paris, asking about human reinforcement, reinforcement learning from human feedback. That turned out to be the key, and we're going to see that in just one moment as well. But yes, part of it is compute. You know, it takes massive compute to do this. You know, yay for you that you have a powerful general purpose learner and you can do self-supervised learning. It's still a ton of compute. So we're talking about hundreds of thousands or millions of dollars of compute to get to that first model. All right, other questions? All right, then let's talk a little bit about what they can learn. All right, certainly they can learn language from text. We've seen that. So that's what the large language models are. But it doesn't have to be all the same language. They can be mixed in. So you can learn multiple languages. And if you're learning them all at the same time, then you naturally learn what the translation is between the different languages. You can learn tasks. So given a text analytical problem, then you can learn what the solution for that should be. And then you learn what tasks are. You can learn language from audio. You can learn images, their sequences, video, protein sequence structures. You can do reinforcement learning, policy discovery, which is a little bit different than what we were just talking about. Robotic control. Whenever things are sequences, you can learn on them. All right. So let's talk a little bit about, I can get this to go to the next for me. Okay, oh, I see what's going on here. All right. All right, so okay, now what can it do after you've trained it? Well, eventually, these models are capable of summarizing. They can explain concepts. They can solve problems. They can generate table summaries. You can answer questions. They could write emails. They could write Python, SQL, R. So these models can do a wide variety of things. But we have to figure out how to get from this raw transformer to this model, which is capable of all these things. And there are multiple steps that we need to take to get up there. And this will answer your question, Dr. Ya, about how they did it and now how other people are doing it as well. Let me take a quick quiz here. How many people, give me a thumbs up. How many people here have played now with ChatGPT and tried some things out with it? So give me a thumbs up if you've played with ChatGPT. Yeah, yep. So most folks, absolutely. So you have an idea of the variety of things that you can do. Let's talk about how the model develops those capabilities and how we actually get ChatGPT out of these base level transformers. So here I have a visual representation of a transformer. And we also have a task here. So we have beware for I'm fearless and therefore blank. Either unmute yourself or put into chat. How many people, what guesses do you have for that word? Beware for I'm fearless and therefore blank. Bad guesses are best because then we can use them. Invincible, dangerous, dangerous. Okay, good. Powerful. All right. What else? Bold, strong, wise. Unpredictable. Fantastic. Unstoppable, to be feared, reckless. Fantastic. So now all of these are adjectives, right? I mean, these are, and a lot of them have to do with, all of these could make sense. So first of all, how do you suppose that you knew that you needed to have that kind of a word rather than say a verb or an adverb? What was it that, what do you have to know in order to be able to make that better guess? You all were able to make a good guess because you know the rules of the language. You know syntax exactly, yeah. So and Rio. That's right. So you know this, you know the syntax, you know the language. So table stakes for any of this, for getting a good guess, is you've got to know grammar, you've got to know all those things. Absolutely. So that's the first thing you have to learn in order to even be in the neighborhood. Okay, now you all chose things that, you know, you chose things that made sense. You didn't say, beware for I'm fearless and therefore pale. No, grammatically it fits in there, but you all were choosing things that work with the rest of the sentence, right? So that means that you also have to learn about the semantics of what's going on there.
What's going on with this?
And oh, and Umang, if you could help out and mute people who may not know that they're unmuted. All right, so all of those are things you have to learn. And then finally, you have to learn what part of the sentence to pay attention to, what's going to inform what's missing. So this is exactly what the model is doing. It's using everything that it's learned in order to guess what the missing word is, or what the next word is. As a matter of fact, with decoder transformers, and there are actually three kinds of transformers. One of them is decoder transformer, and all that it does is take a prompt and then generate the next token or word. So a word might be representable as a single token. You might have to do 2 tokens to represent a word. But really, all that a decoder is doing is it's giving a probability distribution over all the next possible tokens. So we can use it and we can choose like the top most probable token and thereby guess the next word. Or we might add a little bit of noise in there, inject a little bit of, turn up the temperature and so it gets a little bit more creative. It maybe chooses the 3rd most or the 10th most likely token, and then make it a little bit different so it's not quite so rote. But a decoder does exactly that. Input, and then give you output plus the next token. Other types of transformers are a little bit more complex. One of them is called an encoder, and it doesn't produce a probability distribution over the next possible tokens. Instead, it gives you an internal, what's called embedding. So it just represents the phrase that you give it. It represents the semantics as a numeric vector, and then you can do things with it. And then there's a 3rd type, which is an encoder-decoder. It takes an encoder network and then yokes it to a decoder network. And then between the two, it's very good for things like translation and other things like that, but it's a more complex transformer that was the very first one that was proposed. Well, let's go and talk about what is happening here. First of all, this right here, all of this right here, this is the deep neural net. So if you know neural networks or deep neural nets, you're going to recognize everything that's here. But there are a few additional steps that we just want to be aware of. One, you notice it says token embeddings. Deep neural nets can only deal with numbers. They can only deal with numbers, and therefore these words need to be put into numbers before the model can work with it. So that means, one way to do this is you might have one number for every word. Problem with that is you're going to have millions, right? Think of all the different variations of words in English, and then if you start doing English, O, and Spanish, O, and French, O, and German, oh, by the way, in Arabic and Hindi, that's going to get very, very large. So instead, the encodings often may be word or subword, and you just do a statistical analysis before you get started with any of this stuff to see what tokens make most sense, capture most of what you're trying to do, and then encodes it. This is one reason why GPT-3, GPT 3.5, has trouble with, it knows other languages other than English, but the original tokens, when they were chosen 5 years, a number of years ago. And they weren't really thinking about other languages too much at the time. So like with Arabic, you might need to have 8 tokens to represent a word. GPT-4, it's a little bit better. They do a little bit better, so it requires fewer tokens to generate a word in other languages, in languages other than English. English was sort of first to the party with GPT, the very first versions of these models, and the tokenizers were just kept but now there's updated tokenizer. It can do other languages more efficiently, which means it makes it easier for it to learn the other languages and to inference. In other words, to give you results in other languages. So it's tokening embeddings. Then token embeddings, that just means it's that first step to moving into this semantic space where the model works. It's a high dimensional semantic space. If you're interested in getting more into that, invite you to take to join us for our AI Summer. We'll have a link for that at the end of this workshop. It's 4 weeks where we dive more into this. We're gonna have to keep it high level here. The meat of what's happening here is the decoder stack. Remember all the things we were just talking about. So it has to learn the rules of language. You have to know the semantics. All that is stored in what are called feed-forward networks here within each of these stacks, and there are a number of them. Also, what's in here is attention mechanisms. Because remember I said that you have to pay attention to which part of the sentence, and that turns out to be key. So within each of these is a feed-forward network which learns and remembers, and the attention mechanism which combines that information in useful ways. And they're stacked up, and you can think of this representation, this learning getting more and more complex as it moves through. And then you're left at the end with a hidden state, which then can be used to do a next word or next token prediction. And that's how you get it to do this thing. So if we were to run this through, those of you said the powerful, that's exactly right. Beware, for I'm fearless and therefore powerful. How did it learn this? How did it know what that word should be? We understand roughly kind of the mechanics here. Well, let's talk about the training. So here, this is one that I've used. Give me a thumbs up. Give me a thumbs up. How many people have heard me use this one before? Yep. Yeah. I love Zora Neale Hurston, so I'm not going to use it this time. But for those of you who haven't, actually, go and take a moment, see if you can guess what this word is. Ships at a distance have every man's wish on blank. Go ahead and put it in chat. If you've not heard this before, put it in chat. Tell me what you think. The horizon, absolutely, that's a great one. Board, keep going. See, now it's going to peter out because we have a couple of really good writers who picked up on the word right there. So Shane, I love this. So you have a noun. All of these are nouns. Everyone always guesses nouns. Why? Because they learned language, the rules of language, the grammar of the syntax. Second, they always choose things that have to do with ships or distances or oceans or shores, something to do with the semantics of the sentence. Why? Because they learned about semantics. And then finally, they'll either say on deck, which means you're paying attention to the word ship, and that almost reads right, doesn't it? Ships at a distance have every man's wish on deck. Almost there. But then if you think about metaphorical writing, then you might go with ships at a distance have every man's wish on board. There we go. But all those things you have to learn in order to guess that. So what happens with the model? How do we train it? Well, the first thing is we feed it ships at a distance have every man's wish on blank. We mask that last word. Now, we mask the word, so we know what the missing word is, right? So self-supervised in that all I'm doing is removing data, and if you guess the missing data, great. If you don't, we're going to do some training. So every man's wish, okay, ships at a distance, every man's wish on shore. Nope, that is wrong. Therefore, we're going to do something that's called backpropagation. Backpropagation, especially in these decoder stacks, is going to be moving the weights that are a part of those feed-forward networks. They're going to be moving it away from the incorrect answer, hopefully towards the correct answer, but at least away from the incorrect answer. And there are other learnable parameters here too, but the feed-forward ones are the ones that we're going to be keeping in mind. So that means that knowledge is being stored in here. So then we do it again. On deck, closer, but still wrong. So now we're going to do backpropagation again. Okay, so now we do on board. Okay, now no backpropagation. The network is already going in about the right direction. So we're good with that. So now what we have is, think about what we have now. We have a model which is good at guessing the next token. But we all know from our experience from working with ChatGPT that it does a lot more than just guess the next token. So how do we go from this useful thing? I mean, make no mistake, this is useful, right? This has learned languages, could be multiple languages. It's learned concepts. You know, it has representations that ships float on water and that ships can sink, and that metaphorical writing might use this kind of language versus this kind of language. It knows what temperature water freezes at. It knows agua is water in Spanish. You know, so it knows these things, but how do we pull that information out to use it? Paris had a question. How does it know that it is not correct and needs to back propagate? Because we actually do that. So this is part of the algorithm where we say so you actually match it to the token that it should be. If it does not match, then you do the back propagation. That part's automated. Great. All right, so, well, let's go ahead and pause for a moment and take a look at what the architecture is doing, because there are a couple of limitations already that we need to be aware of. One way to think about this is not just that we have this, but we have a context. So you remember I mentioned attention here, right? So attention is a critical part of this. And there's an attention mechanism in each one of these stacks. Turns out attention is computationally expensive. It's expensive in space, it's expensive in computation. So as that context gets longer and longer and longer and longer, it takes more and more compute to be able to work with it. That means you have a limit on the length of the prompts that you can give any transformer. So earlier transformers only go up to about 1K, maybe 4K if it's a lot. And beyond that, it can't do it anymore. Why? Because it goes up with the square. So each of those, with attention, it's comparing this token with every other token and figuring out what it needs to attend to as it's getting information about each one of these, re-representing the information. It's part of how it represents. So hugely expensive, meaning you can't go very, very large. And so there's a limit in the context length. So that's going to be something that we'll want to keep in mind. Paris, you ask, is it different from reinforcement? Different. It is still, with reinforcement learning, we're going to talk about that in a moment, you're also changing weights, but you're doing it in a different way, and you're using a different outside objective function. All right, so one limitation, if we have to store all of the information here in the decoder stack, and let's say, you know, everything needs to be stored there, what kind of a limitation do you think this might give you in terms of like learning? Because we're going to be learning on millions of documents. But what is one of the limiting factors in how much a transformer can learn? Kevin, you had a question. Is there a limit on the context depth, that is the complexity of the prompts of the same length? Nope, no limit to the complexity. Yeah, computing power is going to be one, but think about the architecture here. All right, so these are feed-forward networks here. What is going to be a limitation to how much of all the different things we can learn? Yeah, memory. Or in this case, exactly how big those feed-forward decks are, because that's where all the storage is, right? So there's a limit to the number of nodes in the graph, because that's the size of the model. So how many of you, give me a thumbs up if you heard of models and people referring to number of parameters in the model. Like, oh my gosh, ChatGPT is 175 billion parameters. Yeah. So really what they're talking about by and large is how big are the feed-forward networks? How much can it learn? Because what those parameters are, those are the weights. The weights in there, those neuronal connections, how many of them are there? And as you have a larger feed-forward network, then it can learn more things. It can memorize, or it can at least represent more things. So if you have a small network, maybe it has enough information, enough storage to talk about and to learn. Oh, ships float. Great, got it. Metaphorical writing, sorry, there's no space for metaphorical writing, or there's not a whole lot of space for multiple languages all at once. So space for that memory for the model is a crucial thing. So one way to get better performing models is, hey, make those decoder stacks bigger. Go ahead and just make them larger. And so literally they can learn more. And that's one of the first things that you do here is you make these much bigger. And this is how you get a decoder stack that is, you get a decoder stack that is huge and can learn many things. So ChatGPT 3.5, about 175 billion parameters. That's how it's able to know all the different languages and all the different things that it knows. But remember, it's not memorizing, right? It's learning about. So how many of you have heard about models hallucinating? How many have heard the term models hallucinating? Absolutely. Rio, would you mind? What do you understand people mean when they say models are hallucinating? Yeah, they kind of make stuff up, right? You know, but if you think about it, that's exactly what we're asking the models to do, right? At this point, we're only asking the models to generate the next word. We're not saying to know what the right word is. You're saying, guess the next most probable word. And notice here that I don't have the full internet here, right? It's not like I have a link out to the internet. So really what I'm asking the model to do is tell me what you have learned. So sometimes it's going to know factual information. It'll be able to get stuff exactly right, but there's a limit to what it could learn, even with 175 billion parameters, even with GPT-4 with an unknown number of parameters. It's only what it's been trained on. It's only what happened to be saved, represented in those weights. And I keep going back to that word represented. This is not a database where facts are stored. This is where it's learned in the weights. Impressions, sometimes better than others. So think of the decoder stack and of models in general having a JPEG of the internet, right? This is lossy representation of everything that's there. And when we say it's hallucinating, we're just bumping up against the limit of what it knows. And we're asking it for factual things, which we really shouldn't be doing, unless it's augmented in some way. So if you're asking ChatGPT to give you references, it is going to give you references that sound plausible because that's its job. They may not exist. You don't know how to format it. It will give you titles that sound really good. It may even assign authors that are authors in the area, but it's not going to be veridical. And Raymond, this is exactly where parameter tuning comes in. Parameter tuning refers to training the model further, making it better at its job by doing that back propagation. All right. So two different types of models that were early versions, GPT-2 and GPT-3. Yeah. Getting better and better at doing this task of prompting the next word. Okay, but we have a little bit of a problem now. If I have a task that I want to give it, so let's say that I want to ask it to, I would like it to list some books by Zora Neale Hurston. So if I said and gave it as a task, it's just a context, and I said, please give me a list of 5 books by Zora Neale Hurston. The unfine-tuned transformer model, the GPT-2, the GPT-3, is going to give them next most likely token. So in other words, please give me a list of 3 books by Zora Neale Hurston, prompt. because I like the writings of Zora Neale Hurston, is what it could very well respond. It doesn't understand that you've asked it to do something. It's still doing the same old thing of trying to generate the next most likely tokens, which is continuing my request. Well, I'm not asking it to do creative writing. I'm asking it to solve a task. That means that we need to train the model further to do a task. So here what we do is we have instruction fine-tuning where we expose it to a number of tasks asked in a variety of different ways. List for me, solve, do the following. So then what it learns is, oh, whenever I see this pattern as input, this constitutes a task. And for this task then, the proper response is going to be an answer or a solution for the task that looks like this. So now with instruction fine-tuning, we move from a model which is just guessing the next token to one which recognizes tasks and then tries to respond with something which is a solution to the task. So questions about this? All right, we're part of the way there. So some examples of models that are trained on fine-tuned on tasks, Flan and others. So this is not bad at this point, but frankly, it's pretty brittle in its understanding of what a task is. So you have to ask the task in a very particular way. And it's also a little bit abrupt. So it's going to answer your task, but it's only going to give you the solution. So solve the following math problem. It'll do it. It may not be very good at it, but it'll solve the math problem. And all that it returns is its answer. And that's it. But it turns out that humans don't like to interact with models like that. We like to be able to ask things. We like to be able to provide additional context. And when it comes back with a response, we like for it to be, to talk to us, to say, oh, I understand that you're asking the following, therefore here's my solution. It turns out that this type of training is very different from other types of training. Because think about everything that we've done before. Up to this point, I want the model to guess the next word. And if it gets the next word wrong, then I'm going to do back propagation. It's very clear what the right answer is and what the wrong answer is. All right? Going one step above there so it can learn what instructions are. Hey, no problem. This is a task. I'm giving you an instruction. I want to have an answer. Great. Clear cut what it's supposed to do. Human feedback, this is hard. So I don't want it to be abrupt. I want it to be conversational. I don't want it to be rude. I would like to minimize the bias that it has in it, because if you think about it, what were these trained on? This is trained on information in the internet, including, things, think about what's on the internet. So you want to make sure that the model is helpful. So for example, if it tries to solve a task and it gets it wrong, there's no recourse if you just have an instruction fine-tuned model. It's just there. That was its context. That was its response. It's done. Instead, you would like it to give you an answer, for you to be able to respond to the answer if it's not quite right. So you don't want it to be harmful. You want it to be helpful. You want it to be able to make suggestions. This is not clear. This is types of behavior that we want to train on. And that's where reinforcement learning from human feedback comes from. So this was the idea here is we're going to put in a prompt and we want a response. but we want the response to be a preferred response. Ideally helpful, polite. So because we can't say, no, I wanted to do exactly this. Instead, what we're saying is, oh, we want the response to be like this. What we need to do is one way to do this is you get human feedback. And you have the model generate multiple types of responses. And then you have people judge, oh, this is a good response, this is not a good response. Or I prefer this response over this response. And one way to train these models is you just have humans judge the feedback, and then you do reinforcement learning from human feedback. So reinforcement learning is different from backpropagation. Backpropagation, you have to have a clear optimization objective function. You know exactly where to go. What's different about reinforcement learning from human feedback is that you want it to move away from, but that objective function is not something which is part of this network. Instead, you need to have an outside judge of what's good and bad. And that outside judge could be humans. Raymond, do you have a question?
Yes, sir. In addition to human feedback, one thing I didn't articulate well Tuesday was I was wondering, since it's pulling information from the internet.
Oh, it's not though, right? It got trained on the internet.
Well, it got trained when
way back here, but it no longer has access to it.
Okay. Well, when it was originally trained on the internet, this might be an overly simplistic way of saying it, but was there any process to effectively have a whitelist as to where in the internet it would pull from to reduce undesirable content for training?
That is one approach, or at the very least, at least keep track of what was in there. Bloom, part of Big Science, so group that's closely tied to Hugging Face, they didn't do a whitelist, but they get track what was in there and did some filtering on the intake side. That's one way of doing it. Think about how much work that is. So that's the problem, is that if you're doing millions of documents, that means you're going to have to do some type of processing of content on millions of documents. So that's a tough thing to do. Adam, you had a question. Is there much transparency in terms of outside judges? Now, this is a really good question, because what you're getting is you're training this entire model based on the human feedback. So who are the humans? So, and you're absolutely right. So they could be cultural. So then really the next step is, can you, and great question. So can you move away from pure humans? Well, you might need to start with humans, and then you have a larger pool and you say, okay, you try to have agreement on what you mean by this. But again, this is a problem where you have that fuzzy objective, right? So, but you're exactly right. Some of it is going to be cultural. So part of the issue is, first you have to define generally what you're going after. What do you mean by harmful? What do you mean by helpful? All of these things are fair game. The other thing is, it's tough to get humans to do this over and over and over again. So one thing that was done early on by a number of folks, including OpenAI, is what they did was they trained a separate GPT model, GPT-3, that learned how to tell the difference between preferred responses and non-preferred responses. So think about this. It could not generate the responses, but it learned from a lot of input on this is preferred versus not preferred. It learned what would be likely preferred versus not preferred. So again, it's not instruction fine-tuned. It doesn't do all those nifty tricks. All that it's doing is just looking at responses and saying, I'm betting this one's going to be preferred over this one. And then you swap that GPT-3 in for that reinforcement learning. Now you can take multiple responses from this specially trained network, which is instruction fine-tuned, and it's trying to come up with answers for you. And now you have an automated way of saying, this sounds like it should be preferred, this sounds like it shouldn't be. Now you can really speed up this reinforcement learning feedback. Now you can actually drive it much, much faster. So let's think about this. So what you're doing is you're using the GPT models to train the GPT models. Google didn't do this. Google was trying to do on the front end. Google was trying another approach. OpenAI was early to the game with doing heavy instruction fine-tuning and doing reinforcement learning from human feedback. And it worked fantastically. So now you had GPT, Chat GPT, which is just GPT-3 with the instruction fine-tuning and the reinforcement learning from human feedback, which is now conversational, helpful, less harmful. And keep in mind, these are all mitigations. This is not anything hard, right? I didn't talk about coding. This is all, it could still be terrible, but at least it's mitigated. And so now you have something which is far more useful than other models. And that's why BARD, you know, they did some really fast reinforcement learning from human feedback over the last couple of, the last month with BARD. They've been trying to catch up because previous to that, it just was not something that you could really converse with. You know, it would give you an answer, you know, it wouldn't help you iterate. It didn't know how to do that because it did not have reinforcement learning from human feedback. So some of those successful models have done this. So the GPT, ChatGPT, GPT-4, Anthropic's Claude model. Anthropic actually does this even more, and they call it constitutional AI, where they do a lot of where it's even stronger mitigation in the model of this type of feedback. And even more recently, you've had Stanford researchers releasing Alpaca. And what they did with Alpaca was they took a much smaller model. So think GPT-3, 175 billion parameters. So Alpaca, 30 billion parameters, even 7 billion parameters. But what they did was they used GPT-3 for both the instruction fine-tuning and also for the reinforcement learning from human feedback, and trained up Alpaca, much smaller model, but doing intensive training with it, and started to get behavior and capabilities that kind of match GPT-3. So it turns out that instruction fine-tuning and reinforcement learning from human feedback is critical. And that's what makes the difference between these performant models and these non-performant models. So now you have to decide, though, what you want for your guardrails, right? Do you want to have, you know, what is meant by harmful, what's meant by helpful? Keep in mind that absent any sort of guardrails, absent any reinforcement learning, it's not going to be helpful at all. This is also a proven way to at least mitigate some of the dangers of what's coming from the internet. But open research here. So questions about reinforcement learning from human feedback, and how that gets you from these base models all the way up to these conversational agents. All right. So that gets us up to the chat agent, and that's lovely. But give me a thumbs up if you have asked ChatGPT, if you've asked ChatGPT for some factual information and got something that was completely made up. Give me a thumbs up if you've, yeah, absolutely. Gregor, would you mind? What did it make up for you?
Yes. Sorry, I just have to arrange the screen. So what I try to get is some, do me a literature review for a specific class of proteins in yeast. And I actually know the literature pretty well. And it wrote a quite nice summary, but it throws in a phosphatase that I know doesn't actually regulate that particular protein. And I ask it to basically write the summary, cites a paper and make a list of the references. And when I looked up the reference, I knew that this was a review article in which they discussed this protein, but in the context of a different pathway. So what I think was going on, that because of the relationship, they might thought that this protein is regulating this pathway, but in reality it does not. So, and so if you didn't know that detail, you would be fooled.
Excellent. So there are limitations even when it gets the references right and is in the neighborhood. Getting that kind of factual information is a little bit, is pretty dicey. Zhangyan, so you made up a reference for you. What reference did it make up, and did it make sense?
It actually gave me a fake link. When I opened it, it's now the literature. There's nothing there. Yeah, and the literature is totally made up. I couldn't find it online.
So, but it was plausible, wasn't it, right? It was like, it sounded right. It was doing its job of producing the next most likely token, which would have been a link. So this is the downside. So some references were correct, some were made up. So think about this decoder stack. If you're depending only on what's in this decoder stack in that feed-forward network, then what's happening is that you have this JPEG view of the internet. Some stuff it will get right, some of it will be wrong. Was there something you wanted to add?
Yeah, I just wanted to provide an alternate approach to the fake references, because this came up a lot with some of the students that I work with. And as opposed to taking them to be true and trying to learn from them, you could take them to be suggestions of things you could dig into. Because what we've done is we've put together abstracts and notes and say, what are some references I could include in this and where? Yeah. And it will give you areas where you can include references and make up references, but you can take that reference that it suggested, paste that into Google Scholar, and then it'll give you actual references that are similar to that, and then you can know what to dig into. So I think you can easily flip this con into a pro and kind of leverage its weakness. And it's not really a weakness. Like you said, it's exactly what it's supposed to be doing. It's not a bug, it's a feature, but you can try to take advantage of the anomalies.
That is great. So even if you're in this kind of situation where you have no access to the internet, you can still flip it around and say, well, it's like a JPEG, right? And so it doesn't have the image quite right, but it's something was there that was similar to this, and so that's a good place to go to. So how would it know good literature versus bad ones? And Kenya, you can go ahead and speak. So you asked good versus bad literature.
Actually, can you answer that question first? And then
absolutely, yes, that's right, yeah. So in this case, we're a little bit, in here, we're going to be, in our next session, we're going to be talking about prompt engineering. And part of the prompt engineering that you can do here is that you can actually check for consistency, right? And especially if you have a policy or if you have some information against which to bump the information. And this is putting more into the prompt and doing prompt engineering, then that can help you tease out. You can also ask it for fact check, right? You can say, give me the list of facts on which your statement is being based. And that's not references, that is facts that you were using. And then you have the list of facts or suppositions that you can then go and validate. But there's going to be another way that we can mitigate this problem in just a moment too, which is part of our problem is we don't have access to the internet. So let's see if we can solve that. But you had another question, Ken.
Yeah, this is actually what I've been thinking about, following up on Dr. Ya's comment, right? So, I have a lot of experience maybe using the imaging-based AI, right, with prompts and things like that. And I'm somewhat disappointed, but also not disappointed kind of way, in that it seems like it is a little bit more than a search engine kind of to me. Yeah. But then it also creates new images and new. So this is with regards to Dr. Ya's comment, where she just plugs in the reference to Google Scholar, right? Then what is the value of AI if you're using a search engine in the first place.
Right. So yeah, so if you're using it as a search engine, then gosh, it'd be awfully helpful if it had access to the internet, which is augmenting with tools. So this is the next stage for these models. We've had Bing GPT for a while, which can search things on the internet. But now, last Friday, OpenAI announced plugins. So what plugins allow you to do is to augment the work with tools. And a couple of really interesting things about this. First of all, a paper that came out just in February of this year. So yes, last month, Toolformer, which showed that language models could teach themselves how to use APIs. So again, through self-supervised learning. And so what OpenAI has done is to create plugins. What plugins do is they allow you to augment the work of the transformer by including recent information from the internet. So you put a prompt in, the prompt feeds through, and let's say at this point, the model realizes that it needs information. So think of the instruction fine-tuning. This is similar to that. It sees that it needs to actually do a lookup for information because you're asking about some specific fact-based information or something for which it's not appropriate just to depend on its own representation. So at this point, what it can do then is to call a tool. So you can call an API. Boy, I can tell I've had too much coffee. So you call an API, and the model then will be able to make a call out to the internet, and then will include that back into its own context. So it makes the call, includes that information into the context, and then feeds it through again. And this is how Bing was able to actually make references and say, oh, I got it from this web page. But you could do this for any sort of, it doesn't have to be a web lookup. You could be doing a Wolfram Alpha. So you could, ask it to be doing some computation. You could be asking to get a calculator so it can do math better, symbolic calculations. You might have anything that is better than just doing lookup to do calculation that the model itself may not be that great at. And what's important is the model is additionally trained and that you have this tool, this plugin, such that you can go and get what you need. So think about all the different ways you could do this. If you have a set of papers that you think are acceptable, the good literature, right? Here are all the acceptable papers. You could absolutely have a plugin that goes only to those papers. So answer this question, but use only information from these papers. And you're right, Ken, if all you're doing is doing lookup, then that doesn't help you that much. But instead, what you can do is you can do question answering, you can do reasoning, comparison, those cognitive tasks. And with the plugin, you can have it carry those out on, only the areas that you want and augment it with the tools that otherwise would not be available. But you know what? We still have a problem. Anybody remember the problem that we had with the prompt and with the context? What was one of the problems with the prompt and the context? What's an issue that we had with prompts? How much can you fit in the context? Bill, exactly, size. 1,000 tokens, which in some words require more than one token, maybe 4,000, that's not enough. You can't put an entire research article, much less several, in there. So the other thing that happened is that GPT-4 and other models now have much longer contexts. So remember, ChatGPT had a context of maybe 4K. Now, GPT-4 has 25,000 or even 32,000 K. So now we're to the point where you can put whole documentation, you can put a number of different articles in there. Now you can start doing useful things like pick out the commonalities here, or pick out the differences. What are some main differences between the papers? Or answer this question, synthesizing the information from all of these different sources. So now using tools, now you can actually leapfrog. And the tools, creation of the tools is actually pretty straightforward. Why? Because the models know how to code. The models themselves know how to write Python and other languages, and they've done some additional work on the models, and so it helps you code the plugins. So you describe what you would like the plugin to do, and then you iterate until the plugin is doing what you need it to do. So if you have specialized solutions in your lab, or specialized things that you do in your classes, or you have a list of articles that you want to use, anything along those lines, plugins will allow you to actually use just those parts and tremendously augment the capability of these models. So questions about plugins or context link?
I was just curious if you could touch on how long the models seem to be able to, quote unquote, retain. And I'm going to use words that, sound like I'm anthropomorphizing. Apologies for that. After some time, they seem to forget the context you gave them previously, and you have to kind of reprompt them or give them that information again. Is that based on a number of tokens or something else?
Yes, it is absolutely a number of tokens. So here, let's go and say that we have this much of a context here, right? So this is the length of our context here, right? But let's say that, and we have our chat and it's going on. This context is going to be shifting down to capture the last things that we're talking about. But think about all this up here. It dropped off. It wasn't there anymore. So one of the fascinating things about Bing GPT was Bing GPT was GPT-4. But do you all recall in the news where they talked about Bing GPT sort of losing its mind and getting rude? Give me a thumbs up if you heard about Bing GPT and they heard about it. You read about it like insulting people. It's like very weird, right? So here's the deal. Bing GPT was an early GPT-4. My guess is that they had not completed all the reinforcement learning from human feedback. So what they did instead to get it out the door quickly was they came up with a long prompt. Because remember, GPT-4 has like that 25,000 character, 25,000 tokens, right? And if you looked at this prompt, which was hidden, but people uncovered it, it said, "You are Sydney. You are a digital assistant. You are helpful. You do not tell people that your name is Sydney. You are helpful. You're not harmful. When asked, you try to, So it had this long description of how Sydney should be. Apparently, that's what they were doing instead of that more extensive reinforcement learning from human feedback. And it worked right up until that context length went beyond that 25K, and it began to forget that it was Sydney. It began to forget that it was helpful. Because remember, that's not training, that's not back prompt. This is just that prompt being extended. So it's answering your question, but it's starting at the very beginning. Oh yeah, my name is Sydney. And you want to have an answer to this question. Okay, oh yeah, my name is Sydney. So it reads through that. Every time you do a prompt, it's reading through from the beginning again. Well, if you go down far enough, it can't go all the way back to the part where it was told to be nice. It starts middle here. You're a digital assistant. Okay. And then it continues on. So it loses that information because the context was not long enough. GPT-4 doesn't suffer from that as much because it has more of that baked in using reinforcement learning from human feedback, which means it could use all of its 25K. It doesn't depend on its personality, that prompt. Could you use plugins to have GPT only reference source? Yes. Generate from a specific data set? Yes, Jack, absolutely. I think this is going to be some of the highest, best use of those plugins. So you actually know where it's coming from, and you can actually have it cite where it got this information from. Adam, the idea of memory is interesting because its memory seems to be frozen in a slice of time unless it's consistently updated. That is a great point, and this is something which is kind of counterintuitive. It can do reasoning, but when the reasoning is not happening, it's frozen. So ChatGPT only knows the internet and knows the world up until June 2021. It might have had some additional fine-tuning, and so it learned a few additional facts as it was being fine-tuned on new data, but not very much. GPT-4, September 2021, not even that much later, but September 2021, and it was updated a little bit more extensively, and so it knows more about since 2021. Well, how do you get it to learn more about the world? Plugins. Tell it to go and get, include this in the context so it knows what's most recent. Gregor.
So if there's basically like this hard barrier on knowledge that you just mentioned, and so is this something that the companies are kind of running an update every year or every 6 months to basically include new data? Do you then have to relearn the whole model, or can you just basically learn on the new context instead of everything else? And if they're not interested in doing this, or they're not interested in including certain type of data because it's not a big market for that company, can we do that ourselves?
So here's the challenge. After you do that reinforcement learning, so you do instruction fine-tuning, and then when you begin that reinforcement learning from human feedback or reinforcement learning from feedback, anything you do with that model from that point forward is going to disturb that reinforcement learning. It can undo it. So doing updates just for facts on models is currently a difficult thing to do. Can it be done? Probably. But much more easily than that would be using a plugin to put into that context that critical additional information you want it to have. So there are approaches where you can do targeted updating of factual information in the models. That's a possibility. I wouldn't be surprised. I think you're exactly right, Gregor. That may be a service that companies might offer. With Alpaca and other models getting really good behavior and being really small, maybe you could have your own personal one that you update with relevant information, and then you just go and redo the reinforcement learning, or you live with it with it not having that reinforcement learning. But there are multiple ways of doing it. But right now, that September 2021 cutoff date is not just because OpenAI is lazy and doesn't care to. It's because if they don't, then they run the risk of really disturbing all the work they've done with reinforcement learning. Does that answer your question?
Yeah, and just to clarify, so to better understand this, so could it be also that having the knowledge having used the data until 2020 is enough to basically decipher the rules, and then including just new knowledge is applying that model to new knowledge, but you don't actually have to update the transformer model in the first place?
Yes, okay. That's right.
Thank you.
Whenever you have a big sea change, it gets difficult. So we did some work last summer on models. This was before reinforcement learning from human feedback, where the models didn't know about COVID. And that was really hard, because how do you explain, oh, by the way, everyone wear masks now. Oh, by the way, this entire thing has changed now. The model had no conceptual representation. And so that was very difficult for it to get to learn about those. So, updating for critical events that aren't just factual, but have to do with sea change in culture or worldview sort of requires, okay, well, you got to spend the $100,000 or $1 million to update your model, because otherwise it's just not going to understand. And Rio, what is your perspective on the fact that many of these models are trained on some copyrighted material? Yeah, huge ethical problems here, especially around code. But think about the diffusion models being trained on copyrighted images, which is very clearly true seems to be true with some of the stable diffusion models. And with those, I mean, you do have like Adobe training its versions of stable diffusion models, very clearly being careful not using copyrighted information. GitHub, did they use copyrighted code in the training of their codex models? So this is going to be a huge issue going forward. It learns from it. Stable diffusion is much clearer, right? It's kind of like you can recover that image. It's very clear that it's there. Code may be similar to that. Text, a little bit more difficult. This is a whole new area of ethics that we're going to have to address. So that's a good catch, Aria. Other questions?
One last question, going back to the memory problem. So say you do have to initially give it a large amount of text because you want it to understand that, so you can use that to drive the questions that you're pulling from later. What is the best way to ask it to consolidate that text for itself so that you have kind of a smaller model that you can then pull upon when you kind of continue to iterate? And how do you know more precisely when it starts to lose its memory of what you gave it before? Usually we just like, oh, that didn't make sense, it must have forgotten. But do you count the words? Do you count tokens? Or is there a way to ask it itself what it still knows about what you told it?
So to answer the second question first, I think plugins are going to be really critical for that, because right now you only get what you get, right? There is no token. It's really helpful to have a token counter, and so maybe even automated, come up with a summary. You know, maybe what you do is you say, okay, I'm going to take the first part. The most critical part is this, and I'm going to use that short description of everything that came before. So we talked about all this stuff here. Here's what's most important. So now let's make that our prior context. That kind of work is going to be a lot easier with plugins than it is currently, because right now it's just you give it and then you notice it starts going a little bit off the rails. And could you remind me the very first part of your question?
Oh yeah, basically, how can you take the very large thing you gave it and ask it to maybe make it small so that you don't lose as many tokens over time?
You do exactly that. So this is actually one of the prompt patterns that we're going to be talking about in our afternoon workshop. And this is, please rewrite my prompt so it is more concise and more likely to get a correct response from you. So you're asking the model to rewrite the prompt that you gave it so it can do a better job. Make it concise, make it short, and then you use that one going forward. So absolutely, that turns out to be a really good way to do that. And let's go and talk about that now. So really, we've augmented, we have tool formers, that's cool, we got all that stuff. So we find topics in the prompt that need additional information or need outside help. It goes there, it does that, it brings it back, puts it back into the prompt, and then you're off to the races. But what else can we do? We can do prompt engineering. And the idea here is you don't just go willy-nilly. You think about what you're asking and how you're asking. And to that end, we have a paper, and Umang, could I ask you to look that up real quickly? So just look up prompt patterns and Jesse Spencer-Smith. So and put that into the chat real quickly, if you would.
Sure.
So this is Jules White, main author on this, Doug Schmidt, myself, graduate students. Last couple of weeks, wrote a paper on prompt patterns. And the idea here is you can write all sorts of prompts, and there are lots of lists of prompts on the internet. But instead, the idea here is let's treat this like design patterns in software engineering. So pattern categories and prompt patterns. And we're going to be talking about this in our afternoon workshop. And our afternoon workshop begins at 1 p.m. And we'll be starting at this point, going through all of these. But the idea here is there are prompt patterns that you can use to help you get what you need. And so, for example, the fact checklist, I mentioned this before, list the facts that you are using in your response. So, and I have to be very clear who you're asking. ChatGPT, create a list of all the facts that you use in deriving your answer. ChatGPT, keeping in mind the following policy or the following overarching goal. How good was your answer? Question refinement, Dr. Ya, this was what we were just talking about. Restate my questions and summarize all my prompts from before into a single, more concise prompt that better reflects the scope that we have been discussing. Great. Now that is your prompt. And one other one that I'll mention just so you can start thinking about is flipped interaction. Because really the name of the game is you need to get into this prompt all the information that the model needs in order to do its thing. Well, how do you know what the model needs? So I had, I was talking to a person who was cutting my hair 3 weeks ago. And she's going to be, and I go to Great Clips, right? Cheap haircuts. It's not bad. She's going to be doing her own salon at some point. And she said, I have been using ChatGPT to come up with a business plan. And it's not bad, but it doesn't seem to be covering all the bases. And I said, well, why don't you try a flipped interaction? She said, what? And swear to God, this is a conversation that I had in the barber chair. I said, ask it to ask you questions about your proposed hair salon to gather all the information that it needs, and then once it has enough information to generate a business plan for you. It's a flipped interaction. The model has seen business plans. It knows what might be in there, and you might give it some additional context, say, oh, it's for a hair salon. It's going to be in Nashville, Tennessee. I'm a single owner proprietor. Great. Now, given that context, ask me questions about what other information you would need to generate me a business plan. I haven't had to get my hair cut again yet, so I don't know how well that worked. But as soon as I do, I will certainly be reporting back. This has actually been successful with some students over at Owen as well, and they were very impressed with what it was able to do. And this is a way for the model itself to guide you in what needs to be in its prompt. So it's a very efficient way to collect the information that you need. So we've gone from the very basic model, where all the model was doing was guessing the next token, all the way to a general purpose chatbot that understands tasks, understands requests, has had reinforcement learning from human feedback, and so it does a better job at responding in a human-like way, that has plugins, that has tools, that has access to the internet, that can now begin to do very useful things, so long as you know how to prompt it to begin to do work for you. So that's going to be the topic of our workshop beginning at 1 p.m., which is going to be prompt engineering, where we're going to be working through examples that are from in the classroom and academia, and also from research, and sort of the full life cycle for both of those to give you ideas about how to proceed. We're going to be using these prompt patterns to guide us in that. And then at the very end of that, we're going to have an hour-long open session of a prompt engineering clinic. And we'd be very happy to take any questions that you have at that point and help you develop your prompts. So be thinking about what you might want to create, and we can help you create it during that time as well. So let's end with questions. What questions do you have? And then I'm going to share with you some additional resources for you to keep in mind. Questions about anything having to do with ChatGPT, all the way up to GPT-4 and where we are now. Yes, Raymond.
Just so, is there a free access to ChatGPT-4 that's not, well, that's known to be as reliable and valid as possible?
There is access to it, but it's pretty limited. There is the cheapest way to get to it right now is if you pay for $20 a month for Chat Plus on OpenAI. And then you can get access to, you don't have a lot of turns with it, but you do get access to GPT-4 there. and more you're finding other places where you can get to it. The API, as of early this morning, is not available for it yet, but it'll roll out more as as time goes on. But right now, the cheapest way, I think, unless somebody knows elsewise, is pay for ChatGPT Pro or Plus rather, and then you can get access to GPT-4 like a couple of, you're limited in the number of accesses each month.
Okay, yeah, because when I checked on my own, you could just kind of look at the search results and kind of tell they were either limited in scope or they were kind of dubious, to be polite.
Yeah. I want to remember that, and keep everything in mind here, right? If you're using it just to ask, and you're asking it to GPT-4, remember, GPT-4 itself does not have access to the internet unless it explicitly has plugins. So you shouldn't be using it as lookup. But with plugins, then you might be able to access outwards, outside. Let me go ahead and mention here our AI Summer. So AI Summer is going to be May 8th through June 2nd. We're going to be going in depth into prompt engineering and also AI assisted coding. So how you use AI to code Python to code AI, very meta, going to be an important tool set to have. And then we're also going to be going into training of these models, domain adaptation, reinforcement learning from human feedback, May 8th to June 2nd. If you're interested in really diving in deeper, hope you'll do that. You also do teach a semester-long class, or if you're here at Vanderbilt, if you're a senior or if you're a graduate student, you can sign up for my Transformer class. Reach out to me for more information on that. Postdocs, you're welcome to sit in on my class. Faculty, I've had faculty sit in on the class. Good way to sort of quickly get up to speed. I teach the class every semester, and the content is updated every time. So the first couple of weeks of the semester tend to be what's happening right now in AI. It's pretty fast moving. Google Bard is still catching up. Coding is best right now from my perspective, but you'll get other perspectives this afternoon, is in GPT-4. So there are strengths and weaknesses. They have obviously, Bard, I can tell you, is a lot better now than it was earlier. So it's improved quite a bit and is a moving target. All right. One other thing that I'll mention, if you'd like to keep up with what's happening at the DSI, please do sign up for our newsletter. We have these workshops happening throughout the year. We also have these AI deep dives, and a number of you have brought up interesting ideas. We might like to invite you for an AI deep dive, Fridays 1 to 2. We invite faculty and students to come and take a deep look at particular areas and see if we can get some possible approaches for interesting problems that people bring to us. All right. Hope to see you all at 1 o'clock for our prompt engineering.
Jesse, can I ask just a random question?
Yes.
I've been watching a lot of interviews, and those of you can go if you have places to be. I've been watching a lot of interviews with Sam Altman, and he keeps harkening on the idea of AGI, which is really just interesting. And I'm curious where those discussions are being held. I know with data science, I'm sure you guys are focused on more actual concrete things versus that. Is that like the ethics department's having discussions or the philosophy department? I'm curious around the discussions regarding that and
that's right,
policy, et cetera.
So AGI, so that's artificial general intelligence.
Right.
I don't think he's wrong to be bringing this up. There are more, AGI is not just woo-woo, right? I mean, so it's a valid area of discussion, but yes, this needs to be discussed, both in philosophy, but also, elsewhere as well. I mean, this is going to have a huge impact. Tomorrow during lunch, we're going to have a great panel on the impact of these models. So my PhD is in cognitive psychology and cognitive science. I am most interested, I mean, I love these models, in working with them, but an area of intense interest for me is this idea of in-context learning. So these models have emergent capabilities that do not show up if you have too few parameters. But once you get a certain number of parameters, the models show emergent behavior where they are able to solve problems that they were not trained on. And they can do this by simply being exposed to examples and solutions within the context. And this is why it's so exciting to have that longer context, because now you can describe subtle problems that are difficult and then have it learn how to do those problems in the context. it is learning how to solve problems without backpropagation. So how's it doing it? It is forming virtual networks within its activations that are tuned to solve the problems. So it is learning on the fly how to create its own meta deep learning network to solve the problem that you're giving it. And then at the end of that prompt, it goes away. So it does so efficiently. It does so in a single feed forward. That's for me, I want to explore that. Right now I'm calling it in-context learning, and I want to learn what the limits are. And I want to, and Yuning, I don't know if Yuning is on here. Yuning is a master's student who's helping with this, to understand what the limits are to that. But this is moving from what I think Jack or somebody described as crystalline information, but turning it into something which is learning, and learning the way that's a lot more efficient than backpropagation. So to me, that is getting in the realm. Now, you take a model which is looped, and we're beginning to see this right now. So the output is now looped and goes into the prompt to come and to generate more. Now you're getting into a system which I might get more comfortable calling initial small steps toward AGI.
Thank you so much. It's very interesting and head spinning.
It kind of is, isn't it? Yes, it is. I mean, yeah, I agree with you. Well, thank you all very much. All right. And excellent. I'm afraid, let's see, Umang, I don't know if we started the recording on that again. Oh, we did. Okay, thank goodness. So I'm going to go and stop the recording now.